We're now going to move on to the part of the course that talks about reactive streams. And to begin this discussion, we're going to cover an overview of the reactive streams programming principles, or the reactive programming principles. And you'll discover what they are. They're documented here in this thing called the Reactive Manifesto. I guess these days you can't do something new and different without a manifesto. Actually, there's been manifestos for a long time. The Communist Manifesto, the GNU Manifesto, the Reactive Manifesto. I'm sure there's other manifestos. There's probably an Agile Manifesto as well. And you'll see that the manifesto properties and principles described for reactive programming include responsive, resilient, elastic, and message-driven. So first, quick recap on what reactive programming is. It's an asynchronous programming paradigm. We've seen that before in the context of completable futures. It's concerned with processing streams of data. That's a little different from what completable futures gives you out of the box, although you can combine them with Java streams to get you a stream of asynchronous data. And then reactive programming also works with propagating the changes throughout a stream. And that's also the case with completable futures, but we'll see that with the reactive streams model, which is the focus here, we take the concept of a stream one step further and actually integrate it in with the reactive and asynchronous programming model in ways that completable futures don't give you out of the box without combining them with Java streams. So reactive streams goes one step further and kind of bakes those things together. We use it to compose asynchronous and event-based sequences together using various types of operators. What's kind of funny, in Java streams, we talk about operations. With reactive streams, we talk about operators. They're very, very similar, but I try in my head to remember to use the different terminology because that's how it appears in the documentation. Ideally, the operators that are applied in the context of reactive streams are non-blocking. And non-blocking is a big deal in the context of reactive streams. It gives a lot of power, a lot of flexibility, as long as you understand the paradigm of asynchronous programming and the patterns and best practices therein. The operators in a reactive streams model can be mapped transparently to one or more threads. And there's ways of doing it with built-in thread pools. You can make your own thread pools. There's different kinds of thread pools, as we'll talk about here in just a moment. Programs that are designed using the reactive programming model are going to benefit from avoiding constantly starting and stopping many threads of control. So you'll see that there's all kinds of clever ways where you can represent anything as a data stream that can be created on any thread, functionally transformed and consumed by everyone on any thread, which is just a visual way of saying what is cool about reactive programming. You don't have to keep starting and stopping stuff. Reactive programming is very useful to support certain kinds of scenarios. Processing of user events is a classic example. So, for example, in the context of Android, if you've got mouse movements, well, not mouse movements in Android per se, but touch events, for example, GPS location signals, anything that's event-driven is most likely to benefit nicely from reactive programming because it's event-driven, and therefore you want to be quick and responsive and so on. Responding to and processing latency-bound I/O events to avoid delays and blocking. For example, being able to handle asynchronous network I/O in a pub/sub environment. The example I use here is Twitter messages. So you might have a Twitter feed, and you want to analyze the messages that are flowing through there, the tweets, in order to see what's happening. Are people happy? Are people sad? Et cetera. And another place that you can use events and reactive streams very effectively is when you're communicating between microservices in a modern web-based computing environment. This class probably won't go into this in much detail. The class I'll be teaching next semester, which is the Reactive Scalable Microservices course, will really go into this in quite detail. It's very cool. And we'll end up building some interesting examples and some interesting assignments that have microservices, which are, think of them as little objects that can be essentially deployed to different computing processes. And you can have what's called an API gateway disseminating incoming requests from clients to the microservices running in the back end, and they can go off and do other computations in parallel on different computers. So it's a cool way of scaling things up to take advantage of many core processors or data centers or clusters of some kind. There are 4 key principles in reactive programming. These should be pretty familiar to you by now. There's responsive, which means you want to have rapid and consistent response time. You want to have ideally reliable upper bounds on the time needed to deliver consistent quality of service and prevent delays. You want things to be responsive. You don't want to wait. You don't want to have the spinning hourglass, the spinning wheel, or the hourglass of death and hourglass of delay and so on. You also want your system to be resilient, which means that if something fails, the whole system keeps running and you just find a way to capture the problem and encapsulate the problem and rectify and remedy the problem and so on, so that the failure of some things won't bring the whole thing crashing down. And that, of course, is typically done through exception handling mechanisms. You'd also like the system to be elastic, meaning that it should be responsive even as load grows. And we want to be able to support auto-scaling, which means as the load grows, we just allocate more cores or more processors somehow to make things grow. And then finally, and I mentioned this when we talked about completable futures, you'd like things to be message-driven whenever possible, which is really more of an implementation detail, but it allows loose coupling and location transparency and isolation between components. And this is typically done, as we'll see, more at the implementation level behind a nice method-oriented API with the abstractions we'll be talking about here. There's a whole bunch of frameworks that implement these reactive principles. We're going to talk about RxJava. We're going to talk about Project Reactor. We're going to focus on RxJava in this class, but just be aware that there's other things like Akka streams and reactive databases and all these different mechanisms. We're going to focus again on RxJava, which is got a very interesting history, and we'll talk about that as well. So that's a quick recap of the overview of reactive programming principles.